And I'm not going to list everything. I'm working with basically two of them, the Alexander polynomial and the Jones polynomial. So these are Laurent polynomials and defined long time ago. The easiest way to define them is using scaling relations, and the reason I mentioned them because you can generalize them in a to be bigraded vector spaces, which is like would be not Floer homology. And Combinatorial homology. So these were polynomials. These are bigraded vector spaces. And the relation that if you take the Euler characteristic with respect to one of the gradings, then you get back the Alexander polynomial. So you can take the Euler characteristic. So the ranks of the respective vector spaces. So these ones are defined, like originally defined using holomorphic disks, and these are defined using resolutions of the norm. And what you should think of is that this one is somehow more naturally global invariant. This one can be localized more easily. And what I'm going to show you that you can localize this one too, and it fits into a very similar picture than the localization of this one. And so that's where I'm going. So this one were not invariants, and then I'm going to talk about tangle invariants. Okay? So I didn't draw you a knot, but I'm going to draw you a tangle. Okay? So it's slightly different than what it was for Claudius last time, because I'm not working with four-ended tangles. I'm working with tangles who have two sets of endpoints. So yeah, they are in the 0, 1 cross R2, and I'm also considering them oriented. So. And I'm thinking of them as morphisms in a category. In the following sense that so my objects in the category are going to be sign sequences of points. So this is the sign sequence, plus, plus, minus, and plus. So these are the objects of my category of tangles. And then these are the morphisms. So up to isotopy, fixing the endpoints. This is a formulation of tangles in the sense of Turaev, and when I say that I'm categorifying something, then what I mean that so tangle invariant is going to be simply factored from this category into some other category. And then I'm not going to define anything here for how these invariants are defined. I'm not going to tell you, but I tell you the spirit of it, like how it is defined. For example, for the tangle invariant, which recovers the Jones polynomial as a not invariant. So of course these ones automatically give me some not invariants, because from the empty set to the empty set you do get a not or a link. So if this category is the category of UQSL2 representations, then the construction of Reshetikhin-Turaev gives me automatically a UQSL2 representation associated to any set of points. So P0 and VP1, these are just basically tensors of the vector representation of SL2 corresponding to the set of points of plus, and minus. This is the dual representation. And then in this case it will be just V, and then the Reshetikhin-Turaev invariant gives me a map corresponding to any tangle, which I'm going to denote by G. And then if you compose two tangles, then they compose nicely. So and if you have a closed knot, so let me just draw your closed knot. Okay, so if you have a closed knot, then this one is going from CQ to CQ, and then by Schur's lemma, this is going to be a multiplication by some constant in the field CQ. So that's just multiplying by the Jones polynomial. So this is how you recover Jones polynomial from the Reshetikhin-Turaev invariant. And then what I think this is classical. I don't actually know. Was it Jones already? To say it this way?
I think it's Reshetikhin-Turaev.
That's Reshetikhin-Turaev. Okay. And then Kovanov lifted the whole thing up to graded rings. So this is a work of Kovanov. So instead of vector spaces, he associated graded rings to sets of points. And then for a tangle, he associated bimodules over these graded rings. And that's it, they compose nicely. So if you have two of them, then tensor. And if you do it for a closed knot, then you end up having a trivial bimodule over CQ, which is just covariant homology. Associated to the law. And the connection between them, here we know what's the connection. We take the Euler characteristic and then we get back the Jones polynomial. And here, if you take the Grothendieck group, then of this one, then you get back these vector spaces. So this is Grothendieck group. And tensoring with this bimodule gives me multiplication with this element if we lift it up to the Grothendieck group. So tensoring with the T corresponds to the multiplication, corresponds to the G of T. And that's it. So that's the picture for the Jones polynomial and Covenant homology. And the moral of my story is that you have the exact same picture for Petkova homology and the Alexander polynomial, which is somehow, I don't know. When I entered the field, I thought that this was the question people wanted to answer. So I'm happy it's sort of done. It's not as satisfying as it could be, but good enough. So if you take UQGL1 representation,
you should define people.
Hmm?
You should define people.
I should define what?
People.
P?
Good definition.
It just means which people like it.
So I was in this summer school in Park City. Yes. I was in the summer school in Park City, and then that's where I first saw Ozsv and Szab, actually probably just Szab, and he told me. That's what people mean in this case. So the Reshetikhin-Turaev construction is very similar, except that it's this map is, this interliner is defined a little bit more complicated because it's not so automatically braided category, but we're totally gonna ignore that fact, okay? So you again just take the vector representation, and for any set of points, you define UP0 and UP1, again as just the vector representation, tensors of vector representations. I'm not even going to write this. So this is again just the two-dimensional representation of UQGL1. Yes, and then corresponding to this, there is this interliner Q of T, which composes nicely. Okay, I'm just putting a circle here, and which for a closed knot gives 0. So that's not so nice, but it's almost working because if you open up your knot just a tiny bit, then you get a map between these two-dimensional representations, and that when you multiply, this is again just a multiplication by some element, and that element is gives me the Alexander polynomial. It's just the Alexander polynomial. I didn't think of this notation.
So, I mean, is Hom VV one-dimensional, or is there some?
Now that's the sure lemma, because it has a GL11 action as well, and it's equivariant.
Right, I see.
So yes. So it's a diagonal, and then has to. It's a multiplication. And then what we did in a Petkova is that for any set of points we define, and things just get more and more complicated as you go here. So we define these are not anymore graded rings. They actually have differential as well. So it's a differential graded algebra. Okay, and then over this differential graded algebra, we have differential graded bimodules, which are differential graded bimodules. But if you think of them as A-infinity bimodules, you will see it for in a second why. Yeah, the reason is that when you multiply, when you compose tangles, then you end up having to take a derived tensor product of them. So and up to some stabilisation. This is true. And then this being 0 means that you probably don't want to get back not for homology or for not in this case. But what you're going to get back is almost not for homology though, is the chain complex corresponding not for homology of a knot union a completely independent tangle. It's just floating somewhere. And that is the same thing as of the knot tensored with F2. These are the two element fields. And then the grading of this one is minus half, grading of that one is half. So it really, when you take the Allen characteristic, this is going to give you 0. It's actually, for me, that's the only proof I know that this is 0, which is probably sad, but that's what I can say. And then, yeah, that's basically all our results. So it does recover not for homology, just there is this trivial factor which kills everything later. And
So
then
So you made some comment about that being true up to stabilization. Can you say more what that means?
yeah, it's just, so this one, you can freely tensor product this, basically something with this, something like this, with different gradings.
But at the sort of, at the end of the day, I always get CFK of K tensor U rather than K tensor some number of unknots.
Yes.
Okay.
So basically, the only problem here is that what you associate to the straight tangle is somehow not an identity here. It's I think I don't remember. I think it's F2 plus F2, but I don't remember. I don't remember the gradings.
But
In some
so like,
gradings. And
I mean,
this is what the stabilization gives you.
okay.
But it leaves really in the field, so that it's like, so you can really read off everything. It's not. It looks like a complication, but I mean that's just as bad as CFK tilde is.
Sure.
Yes.
Yeah. Okay.
It's not worse than that.
Yes. Okay. So
So the thing you associate to the identity tangle
Yes.
is not the identity bimodule?
If you just blindly compute it, no. But of course you can define. I mean, it's some factor of this. Well, some. Yeah. So we probably have to factor out with this relation that anything which is the tensor power to something is the identity. I mean, you can also define it that it is the identity diagonal, but that never comes up in any computation I'm going to give you. The simplest computation gives me this. The second simplest gives me tensor to the 2, and then there is a sequence of identity tangles, each of them with one. Maybe you will see, because I'm decomposing everything to elementary tangles, but yeah. And if I decompose this one to 0, then I get the identity. If I decompose it into 10 elementary tangles, which are all just straight ones, then I will get to the tensor of the identity tangles. This is actually not an important point, though. It's just an anomaly of the picture. It would. So I might talk about this. So this one has a minus version, which all the definitions we say work, except we cannot prove that it's independent of the tangle. And once we work in the minus version, this doesn't come. So it's just because we are not yet done. Okay. And then, so this one was with Petkova. And then we have the exact same relation up here. So if you take the Gertende group corresponding to these differential braided algebras, then you get better vector representations, and the Qt corresponds to derived tensoring with Ct of t. And then probably what I should mention, so these ones are UQG abnormal representations, which is whatever that is. Or like as I wrote it, this is just a two-dimensional vector space, and then this map only sees the two-dimensional vector space dimension, but there is also some maps here which are lifting the UQG abnormal actions as well. Okay? That's probably the case here too.
Not quite. That just
No?
no.
No, it's not.
Well, if H's are Kavanov's arc algebras, then that just categorifies the components of the trivial representation instead. So you have to build some slightly more complicated algebras if you want to see the SL2 action.
Okay, that's surprising. Okay. And then now I think that this construction is really coming from Floer homology. And that's not really going to be visible from my talk. It's some version of grid diagrams which I'm working with, which is also not going to be visible. I'm going to describe you the algebra completely independently of how it's originally defined. It has a very nice combinatorial description which can be fit in this talk. So A associated to a set of points P. I'm just going to draw pictures. So let's take the original picture. So P equals the sequence plus minus. Then I'm going to take forward, backwards for plus minus, and I'm putting dots to separate the endpoints on both sides. So it's one more endpoint now. And there. and the generators of my algebra are going to be partial bijections between these two sets of points. So partial means that only some of them are paired, and then bijection means that the ones who are paired are just paired to ones. Something like that would be a partial bijection. I'm drawing them, and I don't distinguish between pictures that are isotopic to each other, and I didn't manage to, but I'm trying to draw them to not have triple intersections. And no Reidemeister's removes, that don't make any difference, that would be isotopic as well. And then actually then multiplication. It's really what you think. It's just concatenating these pictures, if you can. And in many cases, it still gives you 0. In many more cases, it gives you 0. So let me just do a bunch of. So the directions are actually not going to be very important in most of the cases. So I want to multiply, for example, this one with this one. Well, that's not working. That's just 0. I'm ignoring the directions for that one. Okay? If I want to multiply this one with this one, then what would I get? I would get this one just going up. And that one, I'm drawing it before and so that one going down and up, which you would think that it.
That doesn't look right.
No? Yeah, not quite. Yeah. Alright. Better? Okay. But still, it's actually, so whenever I see a Reidemeister 2 move, I don't like that. I'm just going to declare this to be 0. So it's concatenation plus a relation saying that if you say Reidemeister 2 move, then it's just 0. Whenever you say a white-white Reidemeister 2 move, you always say a red-red 2. So, but I could write that the Reidemeister 2 between the whites is also 0. And then maybe you want to say something which is non-zero. Basically, when you get you want to get anything which is non-zero, then this one has to continue this. If it went upwards, it has to continue upwards. If it then went downwards, then it has to continue at most, at least not upwards. And then this one would be non-zero. It would give me.
What about the number of white strands can be it can be
Yes.
arbitrary, right?
Arbitrary, yes.
So what about a composition of a single white strand that goes up and then a single white strand that goes down?
That's probably always 0.
So you count, oh, I see, there you go. Thank you.
And then the differential. It's a resolution of intersection points. I'm trying to draw something which is many terms. Okay. So great. So this one would have 3 parts for its differential. I'm working over Z2. And then when I resolve that intersection, then I will get this. When I resolve that intersection point, I get this and this one. Okay, so this one has a right dimension too. I'm killing it. So it's the sum of these two. This is how the differential goes. And the idempotents. But that's not hard to figure out, are the ones which don't do anything for the multiplication, so they are straight strands. There is quite a lot of them. And then, yeah, something like that. So they are one-to-one correspondence with subsets of one more element than how many strands we have. You saw that I didn't use the orientation so far. If I was defining the Minish version, I would have, but I don't. So the orientation is used only to define the gradings. And the gradings are defined just using a number of intersection points, red and white. I'm not writing it down. Yes?
So then, I'm sorry, I must have missed this. The number of red strands and white strands. So P is a sequence of pluses and minuses.
Yes.
And can you say again how the numbers of red and white strands are?
So the red strands is just corresponds. It is, if it's plus plus minus, it's forward, forward, backward. Like each plus is a forward, each minus is a backward.
Okay.
And the white strands is anything.
Your
The number of white strands is
arbitrarily number.
yes.
Okay.
And of course this splits. So if you fix the number of white strands you consider, then nothing goes out of it. Like multiplication you can do in between those, and differential you can also do in between. So the differential doesn't even go out if you fix the end and the starting points. And Tony, can you remind me how you call those? It's the so the number of white strands you are using is the
Oh, you mean it tells you the weight space?
yeah weight space. Thank you. So it stands for weight space. Thank you. I'm really not coming from the right background to talk about this. I'm a Hegel homologist. And so that's why I asked on it. And then our result is that, so it was written down here, but it was not true. I write you the original one. It's a little bit. That's why I said it is not completely satisfying. It has something I'm hoping to be able to remove maybe later. So okay. I mean the definition was okay, but the fact that it recovered the Grothendieck group was okay with the twist, and I'm telling you what the twist is okay, just to be honest. Yeah, so first of all, someone gives you a P, a sign sequence, and for any sign sequence, you can associate an integral weight for UQGL. I'm sort of ignoring what UQGL means, but in this case, it's sort of it is important. So for any integral weight, UQGL has a two-dimensional irreducible Laplace representation, which I will call L of lambda.
And what are the weights?
Sorry?
What are the weights?
The weights are pairs of numbers in C. Okay, it's not for any, but that you have to have that. They are not. They are not equal. I assume that's what you, or maybe the sum of them is not zero. So either not equal or not minus one. So I can actually give you the description of this if anyone cares. And then the statement is the following. So this would be the Grothendieck group of the compact derived category of left differential graded modules over A of P. So it's generated by A of P times E of S, where E of S was just an idempotent. So this was S, and then this whole element is E of S. So meaning that it's generated by those which end on two fixed, or on some fixed set. And K0 So the Grothendieck group is giving you VP tensor L of lambda. What I liked earlier was that it only gave you VP. Okay? So that's the only difference. And then, so if you have your tangle, then, so here's VP 0 and VP1, and then I have also this L of lambda. So for if you have a sign sequence, it actually only depends on the sum of the sign sequence. So lambda for P0 and P1 is going to be the same thing. So I can really label them with L of lambda. So it's a tensor, and then the statement from now on is the simplest, which you can cook out after this problem. So it says that the map under this identification of AP0 to AP1, which you get by tensoring the CT of a tangle, is under this identification in one-to-one correspondence with VP0. Where T prime is just a big tangle. So T is the small tangle. This is T, and then this big one. So when you add the trivial strand afterwards.
Is that the same thing as Q of T tensor the identity, or?
I guess so. Yeah, nothing happens. So, and then this red strand is the one which gives me the unknown. So in some sense it's necessary. It looks like it's necessary. And in some other sense, this statement is not as pretty as it could be. And then, right now, yeah, I have some time, so I'm going to give you. I'm going to give you the UQGL on one action. On this one. The reason I'm not giving you the definition of CT of T is because it's very similar to the definition of the algebra. You just have to include the crossings as well, and it's really like if I only took some simple one, then it would be exactly the algebra, just the red strands would go as the tangle goes. So it's not very different from the algebra's definition, but once you have lots of elementary tangles composed, then because I'm not working with normal tensor product, but I'm working with this direct tensor product, everything gets out of control. Exactly.
But the way you define this CTT is you define it on crossings, cups, and tangles,
Yeah,
and then
you can.
you prove an invariant statement.
Yes. It's still not that pretty. So yes. So it's slightly more complicated than just looking at these ones. Somehow they have two components and you have to treat them differently. So I'm just giving you the statement here. So let's actually theorem again for the same three persons. It says that if you have a sign sequence, then for any of these sign sequence you can define modules EP and FP such that tensoring with these ones gives back E. So when it descends to the Grothendieck group, it is E. And the tensoring with is F. And it squares to 0. The other one too. And then there's another relation in GL11, if you remember, is that EF minus FP is 1. And then that one we have as a distinguished triangle. As a distinguished triangle. So there are some obvious maps here, which I didn't say. But there is a distinguished angle which puts this between these elements, and they are CP equivariant. So and the same for FP. And that's it, and I wanted to draw you a picture of how they are different. How is maybe they just fit here nicely. So I just draw one picture, then we see if it's understandable. So if P is again the same sign sequence, then F of P, so you remember, A of P was just somehow these partial bijections here, and for F of P, I'm just introducing an extra point, and I force this extra point to have a pair chosen from somewhere here. Okay, so I draw an element here, so this one has a pair somewhere, and then the rest is just exactly how it would be for A of So it's a partial bijection with the extra condition that this one has to have a pair. And then E of P, so this was F of P. And then everything else is the same. You can multiply, you can differentiate exact same way. And then for F of P, it's exactly the same thing, except that this guy has to have a pair backwards. Go ahead.
So you're defining a bimodule, an AP prime bimodule.
AP.
Sorry, are you saying it's generated by one element, or are you saying it's generated by all possible diagrams?
All possible diagrams which have this extra condition.
And the extra condition is that the strand emanating from the extra dot has to intersect at least one other white strand?
So there is something which goes from this dot, and it has to go that way. Yes.
And it has to intersect what? What? It has to intersect the
Has
first white
to go.
strand, or the
It has to
first?
go here.
It doesn't matter where.
It doesn't matter where.
So like if I draw all the white strands with no intersections at all.
Just. Yeah. So.
Sorry, I didn't understand.
So that is okay. That would be okay.
So it just has to go somewhere.
Yes.
Okay.
Has to go somewhere, and this one has to go somewhere there. It's a mirror.
So, and you take the bimodule generated by such pictures under the
Yes,
left-hand
exactly.
orientation.
Exactly. So I'm taking a I'm taking a bimodule over AP generated by these pictures, and the bimodule also has multiplication with elements of AP and differential, and they really define it by exactly these pictures there. So, and they do what you expect them to do. They change the weight spaces. They should. It was more efficient than I wanted to. And maybe I say one word about why is it complicated to do different.
This isomorphism there between E, the fact that the CTT commutes with the E, does that take a lot of work to prove, or is that kind of almost immediate from the setup?
So each of these statements are automatic if you work with Hegel homology, and I think all of them except this one we can prove using combinatorics quite easily,
Including that last one up there.
including this in that. Obviously, one of them we cannot, and I don't think it's this one. But in Hegel homology, like when we're using bordered for homology, these are just like obvious statements. Rearranging some Hegel diagrams, which are already the same, and not the same. And maybe I'll just say this one.
Questions? Can you? Oh, go ahead. Sorry to ask you such a trivial example, but can you say again what you were saying about the trivial tangle? So what is the bimodule that you associate to the trivial tangle?
Okay, so I tell you what I associate to any tangle or any like elementary tangle, and unfortunately I somehow. So this is. So I put it here. Oh. So that has to be here for honesty. But it makes it look at as to me. So if someone gives me a tangle, any tangle, then I have to subdivide it into pieces. So let's just repeat the tangle which I erased right from there. So, okay, so you remember the tangle? It was doing one twist, and then another one, and then it turned back, and that's all. Okay. So you subdivide it into elementary tangles. That's easy. But then you don't stop here. Somehow you have to subdivide each of them into tangles so that the positive crossings happen on even places and the negative crossings happen on odd places. And then this one just have to have an extra part. It's unfortunate. So here's where the positive crossings happen. Here's where the negative crossings happen, and it has to start at minus, it has to end at a plus. And then I'm just going to work with only a simple piece. So I have this with the tangle is throughout my whole talk, every tangle should have been red. So I know that it's a positive crossing because of my rule. Okay, so I don't need to draw it. And then my elements here are going to be of the following type. So this one looks very much like the other one. But then here I have to, for any middle piece, I have to include everything I haven't included so far, and I have to go forward with them somehow. It doesn't matter how. Okay, so here everything is occupied, here I choose what is occupied. That somehow makes sure that I'm going from two strands to two things occupied to two things occupied at the end, and that's important. And then somehow the multiplication on the right hand side is really this multiplication. I put there any element from here, and then I multiply it, and I get again an element here, and it's either 0, or if it doesn't have any Reidemeister 2 moves, here what is a Reidemeister 2 move has changed. Like for example, this one here is not a Reidemeister 2 move anymore when I close it up. But otherwise it's really the same. The multiplication is the same. And the differential here is the same. And the differential here is the dual of the differential. So instead of reducing the number of crossings, you introduce new crossings. And then there is a differential, which is somehow associated to exchanging endpoints there. Some of them allowed, some of them are not allowed. And that's it. And so what I associate to the identity tangle is somehow what I associate to this one. And that's why it's more complicated.
Does the differential resolve the red crossings as well?
No.
Okay.
No, I mean the red crossings somehow they are just there.
Mm-hmm.
They correspond to the tangle and they
Oh
don't
yeah,
change.
of course.
Yes.
If I just have, like, in this picture I have a red strand at the bottom.
Yes.
Just sitting there. Is there some sense in which the bimodule that I got from that picture is the tensor product of what happened on the top with what happened on the bottom?
Not really. Yeah, so we have a stacking operation, but that somehow really comes from, again, just from a Hegerford picture, and we don't have a nice interpretation of it in.
I mean, that's not naively true in Combinatorial homology either. It's
Induction or something, right?
it's complicated.
Or
I mean,
Like
the
the
reason it's
bimodule
not
has
true is
satisfy
because,
module, which is the
because of this middle differential that somehow just screws up everything.
I mean, the algebras acting on both sides are,
Sure, okay,
are
yeah.
too big.
Um,
So no, like actually, like when we make the computations and we prove that this is a lift of the Reshetikhin-Turaev invariant, we first prove it for just two strands of a crossing, and then we have to prove that adding a strand doesn't change anything. It's not that automatic. So
right,
it's
so
not
there,
said
so there
that-
is some operation that adding a strand corresponds to,
So on the level of Euler characteristic or Grothendieck group is just multiplying with 1 minus q to the something like that. So yes, but then it already happens in the Descartes verification, which is not so surprising. I mean that there is something there.
is it, so is it possible to get, so for example, if I were to think about the the triply graded Humfley homology, then there's some sort of exact triangle relating, the crossing and the resolve diagram and this other diagram where I draw a thick edge between, I mean, is there
We're not.
any analog of that?
I mean, there is, so that whatever is true in Hegel and not for homology, somehow can be proved here too. I think. So if there's a scaling exact sequence or an oriented, but there's an unoriented scaling exact sequence, so I think that can be proved. The unoriented is even proven by, I think, Ina and Wang. And the other one is just, I think, it's just a lack of interest. I mean, it is possible. Like somehow, these are really coming from grid diagrams, and whatever you can do with grid diagram, you can do here.
So these diagrams don't have to be braid-like, right? So you also have some bimodulo associated to the cup and cap?
Yes, yes, they are. And actually, naturally, they somehow, like in the Hegafler picture, they naturally come from bridge diagrams. So when we prove that it's the same as Nopfer homology, we use bridge diagrams. Like, when they are closed up like this instead of like that.
So is Reidemeister 2, does Reidemeister 2 hold on the nose, or is this again up to some stabilization?
That one holds on the nose, I think. I mean, if you put it in the right place, yes. So if you do it here, yeah, that's true. So that the tangle associated to this
So if,
and the straight one is the same.
so if I draw these two columns with a red crossing and then another red crossing, that bimodulo is like quasi-isomorphic to the
Straight one, yes. And that's, so to be honest, so the proof of it again uses border for homology, like holomorphic curve techniques. And there has to be a proof which is combinatorial, but we don't want it. So that's the reason the minus version doesn't work, because the minus version does not have, border for homology doesn't have a minus version. But because this is combinatorial, it probably has a minus version, which with the right techniques you could prove that it's invariant.
What is the minus, can you say like a word about
Yes,
how the minus
yes,
version
so-
looks?
Minus version is basically that each strand has a numbering. I lost my red, so it's green. So each of these strands are numbered, so 1, 2, 3. Okay, actually, it's only important to number the ones which are going forward. And then the rule that if you go backwards, that's 0. But if you make a Reidemeister 2 move with the one which goes forward, then it's not 0 anymore. It's u, like the variable corresponding to this element, maybe u2 if this was strand 2. times straight. So, and it's
All right, let's thank Vera again.